Okay. Here we have, okay, by the way, these, as you see, these notes are old, but yeah, but I looked at them and they're good. They're still valid. Now, let me remind you what from approximation theory, the Taylor series. So if you have a function from Rn to Rm, and by the way, you can generally think in terms of m as being one dimension, because basically when it's Rn to multiple outputs, it's just basically one at a time is what you're really going to be dealing with. So now when you want to do a linear approximation at a point x naught, then that linear approximation is expressed in this fashion. You have the value of the function at x naught, and then you take the gradient of f in the x variable times the difference between x and x naught. That's a linear approximation. And this is a quadratic approximation. So like in a multivariate x case, the f sub x is a gradient, and this is also this is a row. Think of it, this is a row vector and this is a column vector, so that you end up with a scalar. Now then, in a quadratic approximation, this is a Hessian. And so then this is x minus x0 transpose is a row vector times a matrix times a column vector. So that will also be a scalar. By the way, when you get into doing serious things, you leave this and go into what's called Einstein notation, with upper and lower indices. I'm not going to expose you to that today. And so what happens is that you take a Taylor series approximation is just this multivariate Taylor series expansion. And also I remind you that a function, we talked about a function is analytic if it in some neighborhoods equals the power series. And then if it's analytic, then locally a function equals its infinite term Taylor series expansion. But then we truncate that to get a degree n approximation. Now that's Taylor series, it's a Taylor theorem. Now, here's the implicit function theorem. Now, by the way, here, m being, you can't just look at the case of m being 1. Here, what you have is an implicit function. So, it's okay. So big H takes an n-dimensional x, and then h of x is m-dimensional. So big H has an n-dimensional x, m-dimensional h, and you have an m-dimensional output. Now, the way to think about this is that the big H has m outputs. So the output is m-dimensional. So the equation big H equals 0 is m equations. And so you have this h of x is an m-dimensional function. And so what we're going to try to do is find some, this is an implicit definition of the little h function. This implicitly defines little h. And so you have basically little h is like m unknown functions, and you have m big equations here, and so the number of equations and unknowns matches up. Now, suppose we know the value of little h at some x naught. We know that at x naught that little h is supposed to, that the solution to this, when you plug in x naught, we know the solution here is y naught. Now, what we're going to do is take that information and use that to construct a Taylor series expansion of little h, the implicit function. Now, we do implicit differentiation. So now we take the derivative of this system of equations with respect to x, and we end up with a Jacobian here. This is a Jacobian. This is, you have n x's, and so you take the derivative with respect to the n x's. And here you have also Jacobian, the h with respect to the vector of second arguments. And then the derivative of little h is going to be h sub x as a gradient of h. Now, if you want to find out what this gradient vector is at x naught, you just plug in x naught all through here. And well, the thing is that at x naught, you know what h of x naught is. So you know what this, so you plug in x naught and h and x naught here, then you know this is going to be, then you know this term is going to be y naught as here. This is going to be y naught. And then this is going to be your gradient at x naught. And this is just a system of linear equations. And so basically you have the gradient of little h with respect to the vectors x, the variables x, is equal to the inverse of the gradient or the Jacobian of big H with respect to y times the gradient of Jacobian of big H with respect to x. Now, by the way, hy here, this Jacobian is going to be a square matrix because you have m y's and you have the output of h is m. So this is going to be m equations and m derivatives. So this is going to be a square matrix. So you can invert it. And here's your expression for the Jacobian matrix of little h with respect to x at x naught. And so here's the linear approximation. It's the vector of values at h at x naught plus the Jacobian first order derivatives times the deviation of x minus an x naught. Now, if we wonder about how good that is, we can just take this linear approximation, plug it into here, and see how well it does. By the way, you should take out the units, take a unit-free version of this, and then see how well it does for points close to x naught. Now, one little detail. This inverse, this is an inverse step here. You have to take a matrix, the inverse of a matrix. I'm implicitly assuming that inverse exists. That means that we're implicitly assuming that this Jacobian matrix is not singular. So that is a key step here, that you're assuming that that Jacobian is not singular, and hence you can invert it. Okay. Now, by the way, everything I've shown you here, an example of that is just doing comparative statics in any economic models. Now, suppose that the linear approximation is not satisfactory. Then what you can do is take a second derivative of the implicit relationship. Now you end up with a second derivative of big H with respect to x. Now, by the way, big H gradient with respect to y is a Jacobian. It's a square matrix. What the heck is h sub xx? What the heck is h sub xy? Well, this is now, since you have m equations, and each equation is getting differentiated twice by all the matrix variables, this is actually a three-dimensional object. This is like, you know, one dimension is vector, 2 dimensions matrix, 3 dimensions. That's what that is. Now, by the way, we're now into tensor territory. And this is, you know, if you get this far and you want to do something serious, you You have to learn tensor notation. Now, notice, however, though, that this is the, but at this point, we know what these Jacobians are at x naught. So if we want to know what this second order object is at x naught, then what we do is we gather up all these other terms, and then we hit it with hy inverse. Now, notice, now this matrix has to be non-singular in order for the inverse to exist. But notice, it's the same matrix that has to be inverted to get the second order as you did for first order. This is therefore, this is what we often refer to as a solvability condition. The solvability condition is that this matrix is not singular. And once you have that solvability condition in hand, you can do arbitrary order perturbations. And so this goes on, can go on and on. Now, since I'm not going to do tensor notation, this is going to be the end of this exposition. But the idea here is that when you do a first order perturbation of anything, you will need to have some matrix to be invertible, or some operator, matrix-like operator, to be invertible. But that once you have that invertible for the linear approximation, that same solvability condition gets you through all the other higher order derivatives, assuming that the derivatives of big H exist of high order. So that's the key thing to remember. Now, that was a little clunky kind of multivariate calculus thing to do. Now, here's the basic idea. Suppose you have some parameter epsilon, and then you have some, now think in terms of x being a scalar and epsilon being a scalar. And you want to find some x of, suppose that when epsilon is 0, you know what x naught is, what x0 is. And so but you know that in general, x of epsilon is related to epsilon according to this implicit equation. So what do? You apply implicit differentiation, and now you find out that x prime is the inverse. Now, by the way, this is just the partial derivative of f with respect to the single variable x. And as long as that's not 0, then you can invert. And of course, you can check it now. So here's a linear approximation. And then here's, you can continue for higher order approximations. So x prime was a previous slide, x double prime is here. And this can go on ad infinitum. And that's what you're doing in all of these things. You start with a case where you know the solution, and then you have this parameter and you slightly change the parameter, and then hopefully, f changes in a smooth fashion so that the implicit relationship between x and epsilon also changes in a smooth fashion, and that all these derivatives exist. Now, this is a strategy that's used in all of science, as well as in economics. One example is in general relativity theory. Now, in general relativity theory is really a generalization of special relativity. See, special relativity is just a case where there's no mass in the universe. Or there's time, but basically there's nothing. So, but special relativity is the theory of the universe when there's no mass. So then all of the unknown functions regarding the space-time metric and all that, that's known. That's known from special relativity. So you start with an empty universe, you know the solution to all the equations in general and special relativity. Now what you do is you say, okay, now let's increase the mass a little bit. Let's add a little bit of matter into the universe. And then, now, by the way, the equations of general relativity are quite, well, they look quite forbidding, quite formidable. In fact, one economist made a reference about the equations of general relativity being impenetrable. But as typical of macroeconomists, this guy didn't really know what he was talking about. The equations of general relativity have been solved in various manners, a few cases in closed form, many cases numerically. And this is one of the major ways of solving things numerically. and so the general relativity solutions, yes, they may look forbidding, but formidable, but you can do this in this fashion. And by the way, is that relevant for real life? Well, is GPS relevant for your life? Well, so yes, the satellite and the nature of the satellite signals that give us global positioning system, along with the computations that are done in any GPS receiver on Earth, they have general relativity theory involved in those equations. And if they ignored general relativity, then they would be useless. So the reliability of GPS depends on solving general relativity theory equations. And this is one way to do it, perturbation approach. By the way, some of you may have also heard about some research into gravitational waves. Well, yeah, that's, again, that's how they compute what a gravitational wave should look like. They do a Taylor series expansion. Quantum mechanics, what happens? You start with a case where electrons do not repel each other, solve that out easily. Then epsilon is the force of repulsion, and then you do a Taylor series expansion in that force of repulsion. It's perturbation. By the way, some of you may have heard of Feynman diagrams. Feynman diagrams are just pictures of perturbation methods. That's all they are. Now, in business cycle theory, what do they do? What do you do in business cycle theory? You start with a complicated dynamic stochastic model. Then you shut down all the noises, all the disturbances. And then you look at the steady state. Where does the economy go if there are no shocks to the system? That's the deterministic steady state. And then you say, okay, well, now let's add some noise to this. Let's see what happens as we add noise. And so that's the same attitude. Now, sometimes the standard implicit function theorem may be relevant. Sometimes there isn't one, or in business cycle case, I doubt you've ever seen a theorem justifying what's done. But again, that doesn't matter, because once we have it, we can check the quality. Now, by the way, I've never seen any macro paper doing any perturbation or log linearization where they check the quality, because quality doesn't matter. So, but in terms, if you want to proceed in a valid fashion, you would do the log linearization, do the Taylor series expansion, and then see if it appears to produce a valid answer. And we will, in our examples, do that. So yes, you should always check the solution for the range of validity. Standard practice in macro is no, you don't want to do that. So, okay, this is a continuous time example, which I'm going to start with. So here's it's maximize discount flow of utility. Excuse me. I'm afraid that in a month, given my age, that if I was allowed to venture outside my house, if I sneezed, then I'd be grabbed and taken home. it's interesting, this whole opening up thing. What are they going to end up doing? Basically tell all us old people that because we're susceptible, they're going to protect us by forbidding us to go in public places. We'll see what happens. Okay, so this is dynamic programming, simple dynamic programming problem. Now, the popular idea in macroeconomics is you compute the steady state, convert the nonlinear deterministic problem to a linear quadratic problem. Well, linear quadratic problems are great. We know how to do those things. Linear quadratic regulator, you have seen all those things in macro papers, and then you use your linear quadratic Riccati equation methods to the approximate problem, and then you add noise. Now, that's the ad hoc approach. Now, there's a paper by Ellen McGrattan in 1990 where she defines the linearization approach. And so what she does is she takes the utility function and replaces it with a quadratic approximation around the steady state. So C star is a steady state. You take the utility function, replace that with a quadratic. Here, K dot is f of k minus c. We'll replace f of k with a linear approximation. And then you end up with resulting approximate policy function. Now, though, the problem in her case is that it's wrong. Basically, the McGrattan procedure, if you applied it in general, would give you bad results. Now, the paper has some, page 1 lays out a general method. The rest of the paper applies some examples and shows how it works. However, in the paper, the f of k function, k dot equals f of k minus c, is a linear function. So the linearization here doesn't introduce any optimization error, and so everything's fine. So the examples in our paper are valid. You do have good solution and results. However, these examples are degenerate examples of what's on the first page. In general, that procedure is grossly invalid. And also, I say recent papers, okay, this was done in 2016. Basically, I think they repeat some point about how this is. Now, a lot of your citations go back to Kidlin and Prescott in 1982. And what they do there is that they've first replace the law of motion with a linear law of motion and then do things, and then that's okay. But the thing is that nobody, Kidlin and Prescott nor McGrattan, provide any mathematical basis for what they're doing. They're basically ad hoc methods. Now, when they are valid, they really are special cases of a paper by Michael McGill in JET in 1977. And he does cite the relevant mathematical foundations. Now, by the way, what I'm going to do, what I'm going to try to do is, first of all, write down this. This now is discrete time. This is continuous time Bellman equation. Sorry for, you haven't seen the continuous time stuff much, but anyway, the notation is much nicer. But here's continuous time Bellman equation. Now, why don't I know it's continuous time? Because it's rho vk. This is really partial v with respect to time, but it's an autonomous problem, so it's rho v equals max of u of c plus v prime times savings. Now, the policy function is defined by this, this first order condition. So basically, okay, so now we have, so the true policy function has to satisfy the first order condition, plus when you plug that into the Bellman equation, it should satisfy the Bellman equation. Now what we're going to do is do the envelope theorem, take derivative of all of this with respect to k, and we find that we get rho v prime equals v double prime f minus e plus v prime f prime. What are the steady state equations? See, basically in steady state, consumption equals output, marginal utility of consumption equals marginal value of capital, and then this is the Bellman equation. This is, yeah, Bellman equation, and this is the envelope condition. So this will give us the steady state values of C star, K star, somewhere in there must be an F prime of K. Oh yeah, basically the thing is that at the steady state, F of K star minus C star is 0, so F prime does equal rho. That comes out of the envelope theorem. Anyway, so then you get K star C star, and you get V K star and V prime K star. Those come out of the steady state. So that's what we know. Now, what we want to do is construct a Taylor series approximation of the unknown consumption function and the value function. That's the objective of perturbation methods. That's also the objective of papers like Michael McGill's. That was also the objective of, in economics, I think one of the first papers to do linearizing around a steady state was by Bob Hall it was in his thesis and published in Review of Economic Studies in, I think, roughly 1971. So those people and me and others like that, their objective is to compute a Taylor series approximation of these unknown functions. That is not the objective of Kydland and Prescott. The objective of Kydland and Prescott is instead to take some nonlinear economy and then find some linear quadratic economy similar to the nonlinear one, and then study that linear quadratic economy. That is the objective of the Kydland-Prescott paper. It is not to approximate, the objective is not to approximate the nonlinear model. How do I know this? I once asked Prescott about this, and then he told me exactly that the objective is not to approximate these things in anything like this. By the way, that was in a letter. So yeah, so that's the difference here. When you hear about people saying, oh, we're doing blah, 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 and you cite Kydland and Prescott, okay, they're not, by the way, they may not know this, but Kydland and Prescott, the objective was not to do a good approximation of the nonlinear model. It was just to come up with something that was tractable to play around with. Everything that I'm doing, people like Michael McGill, and going back to Hall, the objective is to compute approximations of the nonlinear model. Now, so how do we deal with this? We want to do a linear approximation around the steady state. So what we do is we take derivatives of that system and then compute it at the steady state. And then what we end up with, a quadratic equation for the unknown slope of the policy function consumption. And so there's two solutions. Why are the two solutions? Well, this is just a simple Riccati equation. When you linearize around a steady state, you have unstable manifold and stable manifold. And so the Euler equation is valid in both on the stable and unstable manifold. But what we want is just is the stable one, so we choose the one so that C is increasing in K. Now, there was a perception in macroeconomics that perturbation methods of order higher than 1 are considerably more complicated than the traditional linear quadratic case. This was in a paper that Marcet presented at the 1990 World Congress. I was the discussant for that paper, and I took exception to his comments. My comments were published in the publications of the papers at the World Congress in 1990, and I basically said that Marcet was wrong on many matters, in particular this one. Now, so what I'm going to do is I'm just going to take those other equations I had, take derivatives, evaluate a steady state, and what you find out is that the unknowns, we don't know what C double prime is, we don't know what V triple prime is. It turns out that it's a linear set of equations. So Marcet had it exactly wrong. Perturbation methods of order higher than 1 are considerably easier than traditional linear quadratic case. Easier in the sense that linear quadratic step, you have to solve a Riccati equation. Now you just have to solve a linear equation. This is easier conceptually. There may be a lot of these linear equations, but it's linear, so nothing hard about that. And this can go on and on and on. And now then what we want to do is, since marginal utility of consumption should equal marginal value of the capital stock, then we do the error checks. And then this is the picture. This, by the way, is a picture you're going to see many times. So here, this is log base 10 of the Euler equation error, normalized Euler equation error. This is a relative Euler equation error. See, V prime and U prime should equal each other at all capital stocks K. So do 1 minus that, and anything other than 0 is going to be the error. And do log base 10. So what you see is that at the steady state, you have exactly, it's a perfect answer. But then with the linear approximation, the base 10 log base 10 errors explode coming out of K equals 1. And in fact, the errors are bigger than 1% beyond a small, outside of a small interval about the capital stock, about 1, let's say. However, as we have higher and higher order degrees of Taylor series expansions, degree 10, we see that we basically have perfection between like 0.9 and 1.1, and 6 degree accuracy between, I don't know, about 0.7 and 1.3. So the higher order does improve things considerably. Now, so this is just to give you sort of a first example of the of these tools and of these ideas. Now, the problem is that more generally, these, one has to work harder in order to solve out these systems. This is just trivial calculus, trivial. I am now going to show you, now I think next comes the, the Mathematica notebook. Okay, any questions? I got to turn on my chat thing. Any questions or comments here? See, that's the basic idea. You write things down and with respect to some perturbation parameter, and then you expand. This is not the way that it's taught as far as I know, I've seen. So now let me do some more movement. Okay. Okay. Let's do this example here. So now this, let me, okay. Now I will send you a printout of this, but let me make sure this is, yeah. But this has some movies in it, so I want you to see this. Yeah, the cinematic magic that we can do here. Now, do these on your monitors, do these display well, or should I magnify this more? Tell me, because I can up this magnification to 200%. So is this okay? I think okay. Yeah, I think I'll stay with the 200%. Thanks for one person's comment, but I think this should be good enough. Now, we're going to look at a discrete time growth model. And this is going to be just deterministic. This is deterministic with the single capital stock and consumption and yeah, so K is a capital stock. That's the only state variable. Beta is a discount factor. Alpha is the capital share. Where the consumption function is not known. We know the production function. K plus is next period's capital stock. C plus is next period's consumption. So now K plus is going to equal F of K minus C. So net output minus consumption. And C plus will be equal to C of K plus. So C of K is the unknown consumption function. So consumption today is a function of today's capital stock. Consumption tomorrow is a function of tomorrow's capital stock. So it's C of K plus. So now what's the Euler equation? The Euler equation says that marginal utility of consumption today has to equal beta, the discount factor, times marginal utility of consumption tomorrow times the gross marginal product of capital tomorrow. So we're going to do log utility function. This is going to be an annual model, so beta is going to be 90.95. Production function is going to be here this is like 100. This is like a 0% depreciation model. You start with some capital K. I write things in terms of a dummy variable X, but so capital stock plus some constant A times X to some power alpha, which I've set to be 1/4. And I rig up the capital A here, basically the scaling parameters, so that the steady state condition is satisfied at K equals 1. So steady state is 1. This is what the Euler equation looks like then. So this is the Euler equation. Now, by the way, don't spend too much time looking at it. It's pretty ugly. This is just a Mathematica detail here. And then what I'm saying is that now, first of all, I'm going to try to build up the consumption function. What do I know? I know the consumption function at K equals 1 because that's the steady state. And I know that the steady state consumption equals total output minus 1, which is the amount of stuff that's set aside to be capital stock tomorrow. So this is a case. I know the consumption function at K equals 1, and I'm going to build around that. And now I check out my Euler condition equation and my example is satisfied. And then this SOL is going to be a list of solutions. I'm going to build up the solutions. I have the zero derivative of a consumption at K equals 1. Now I'm going to do this. The first, second, etc. Build it up. Now, what am I going to do? Now, this Euler equation must hold for all capital stock. Therefore, its derivative with respect to K must also be true at all values K. Okay? If the Euler equation is true for all k, then I take a derivative and its derivative has to be true for all k. So now we have this lovely equation. Oh, that's nice. This stuff gets really ugly if you actually look at what's going on. Now you might say, well, gee, how is this going to help me? Because yeah, here's C prime of k. I want to know something about C prime of k. But then look at this term. This is C prime. This is C prime at tomorrow's capital stock. So this is C prime, not evaluated at k, but at some other value. How am I going to be able to solve out for C prime? Because I got to, at k, without solving out for C prime at these other values. This looks hopeless. But remember, we're only doing this at the steady state. We're only doing this derivative stuff at the steady state, k equals 1. So now if we put in the steady state conditions into this derivative and simplify it, what do we come out with? Wow, we just come out with an equation that involves only C prime at 1. What's happened? Well, you see, the thing is, at the steady state, this capital stock becomes 1 because so wow, C prime of 1 is its own, but now it's a quadratic equation. If you did now, basically, if you had multiple dimensions to the state, you'd have, this would be a polynomial equation, which, by the way, is another way of expressing a Riccati equation. This is just a one-dimensional Riccati equation. Now, this has to be equal to 0. This is the derivative of the Euler equation at the steady state. It now has to be equal to 0. We solve out for 0 and look at what we get. We get 2 possible values for C1 prime. And again, why do we get 2 possible values? Because there's a stable manifold, unstable manifold, and these correspond to two different eigenvalues. We, of course, want the consumption function to be rising at 1. So this is the true solution. And the value, given the parameterization we have, is 0.11, blah, blah, blah. Now, oh, I see. Now, this is what I probably had. Okay, now, let's look at the second derivative. Okay, apparently I can't get this. It'd be nice to get this reduced. Anyway, as you can see, this is a mess. You don't really want to look at it. Now, however, we want to evaluate. You see, this whole ugly thing is going to be evaluated at the steady state. And look at what happens. Wow, it becomes much simpler. Now, we're trying to solve for C double prime at 1. So C double prime at 1 is here. It's here. It's here. Now, what about the C prime at 1? Well, the thing is, we know what C prime at 1 is because that's what we solved in the first step. So what we do is we plug in the value, what we solved, the value of C1 prime, plug it in, plug in that solution, and then now we get an equation that just will involve the C double prime. And wow, look at this. This is a linear expression now. That's got to be equal to 0. C double prime shows up linearly. Wow, that's great. So we can solve it out, and now C double prime is minus 0.0358. What that says is that the consumption function is slightly concave. So now let's add it to our solution set. Let's keep going. Degree 3 perturbation. Take a third derivative of the Euler equation error, and then plug in all your solutions for C prime 1 and C double prime. You get a linear equation out for C triple prime, and bingo, this is the equation, and now you have the C triple prime. And this is now your cubic expansion. Now this is getting tiresome, so let's just do 15 derivatives. This, by the way, takes less than a minute to do. And now we have down here is the solution for a degree 15 polynomial solution around the steady state. Now what I'm going to do is I'm going to define down here, I'm defining the solution for consumption. I just compute the series. Basically, C sol x comma n is the degree n Taylor series approximation of our consumption solution. So basically, I just take the Taylor series of C out to degree n and then plug these in. This, by the way, is not an efficient way of doing that. But now then, here's the Euler equation error. Now, if what I want to do is I want to come up with a measure of the errors, and I want to take out units. So in particular, oh, okay. Yeah, I want to divide by u. Yeah, this is u prime of c. This norm is 1 over goods. So this is u prime c. So I'm going to divide out by u prime at c everywhere. So now then this will be unit free. And so then I'm going to now define the Euler equation error solution at all of these orders. Now, oh, darn. I thought this was, okay, sorry. I have to, I thought this had been evaluated. So now what I'm going to do is evaluate all these things. Yeah, now you get to see how long it takes. Yeah, so there. Yeah, so now you see everything that I did has now been computed. Now let's get back into slideshow mode. And so now, this is a consumption function. And so now this is the degree 1 approximation is a straight line. Here you see a slight convex function. Here we have something different. Notice what happens as I increase the order. Actually, what's fun is just to watch the movie. Now, things aren't going very well at k equals 2.5 and above. Now, why is that? Well, remember, this problem has a singularity at k equals 0. Because at k equals 0, the marginal product of capital is infinite. Also, at k equals 0, consumption is going to be 0, and marginal utility consumption is going to be infinite. There's a singularity in this problem at k equals 0. We're doing the Taylor series expansion around k equals 1. Therefore, by the theorem about radius of convergence, if you have a singularity at 0 and you're expanding around 1, that means that the best you can hope is that your Taylor series approximation, your power series approximation is valid between 0 and 2. And so what's going on out here says nothing other than what you kind of knew in the first place, is that there's no way you're going to be able to approximate anything by this method for k equals k bigger than 2. So now, what happens to Euler equation errors? Here's the Euler equation error, log base 10. At the linear approximation, you see you have basically no error, but then it rises rapidly and you have substantial error. Now you do the quadratic approximation, that goes down, down, down. Let's watch the movie. Down, down, down. So basically, notice that, of course, you've got the same wacko stuff going on over on the right-hand side of the diagram, but between 0 and 2, the log base 10 errors are moving down monotonically. And I think I've run this, I might have run this out to this, I forget what order, we're up to 15. I think I've run this out to, probably order 25 or so. And, you know, this does amazingly well. Okay, so that's how you proceed. You write down the equation, you write down the equation that's supposed to hold everywhere. You pick a point where you know the solution, and here it's a steady state. And then you take derivative with respect to K, and you'll end up with a Taylor series function, a Taylor series expansion for C of K around that point. So that's what you're doing. Now, any questions? Okay, let me. Now comes okay, any questions? Now we get to the well, come on, what's going on here? Okay. Okay, I want to do full view, but anyway. So this is now what I sent you earlier today. So now what we're going to do is we're going to do perturbation for a simple stochastic AR1 growth model. So this is the bread and butter kind of model in macro. So we have a capital stock again. Now we have a productivity level theta, which is going to follow an autoregressive process, first order autoregressive process. Now we're going to have innovations to theta. So theta is going to go up and down over time. It's going to be have innovations equal to z, and it's going to have, and the innovation is going to have mean zero. It's going to have unit variance, and it's going to be IID over time. Now beta will be the discount factor, alpha is the capital share, of course. Epsilon will be the standard deviation of the productivity innovations, and rho will be the serial correlation. And now what happens is that the consumption function is going to be a function of 3 variables, but we're going to treat them symmetrically. But what the case is that epsilon, you see, K and theta are the state variables of the real problem. Epsilon is not it's a parameter of the economy. So we pick an epsilon, and then that gives us some standard deviation of productivity innovations, and then for that epsilon we have an economy defined. Okay, so we're going to treat K, theta, and epsilon symmetrically as functions. This is something that I am not proving. It's true, but proving that requires some non-trivial function analysis. So K theta is a state variable. Z is an innovation. It's not a state, as you'll see. and epsilon is a parameter defining a specific economy. Now, here we see, okay, so tomorrow's theta, theta plus is you have today's theta, you multiply it by some factor rho, which is going to be less than 1, and then you add some noise to it. Now, so we're going to add epsilon times z. See, epsilon now is scaling the innovations to the productivity parameter. When epsilon is equal to 0, this is a deterministic model. And then as we increase epsilon, we're going to add noise to the theta process. So now the Euler equation error, the Euler equation error, the Euler equation error and the Euler equation, I regard them as the same. So, so now the Euler equation says that marginal utility of consumption today. So if you're in the epsilon economy and today's K is K and today's theta is theta, then marginal utility of consumption today has to equal beta times marginal utility of consumption tomorrow, product tomorrow, et cetera. Now, this may look odd to you because what you're used to seeing is marginal utility of consumption today is equal to the expectation of stuff tomorrow. Now, what I'm going to do here, the kind of the trick is to say, well, that's how it's conventionally written. But what I'm really going to be doing is that the Euler equation error for me says that the expectation of that whole thing is 0, where over the random variable little z. Okay, so that's what I'm going to be talking about, is that the expectation of this whole thing is 0. By the way, this may seem like this is a non-trivial observation. And I have then a utility function, standard utility function, yeah. Okay. Oh, this is the setting for the deterministic problem. Let me see. Okay. Here. So I have this A, which I set so that the deterministic steady state is 1. Now, this should really be written nice in order to keep things. No, anyway. The production function is now f of k comma theta. So k is a capital stock and theta. I have a tendency to write things in terms of dummy variables, but this should be k and theta is equal to your production function, except now then now Cobb-Douglas production function is multiplied by the exponential of theta. So theta is going to be basically a AR1 process that's being kicked around by some disturbance z. And this is going to be the and the productivity parameter is going to be the in the production function will be the exponent of the e to that power. So this is common kind of stuff we do. Now, we check that the Euler equation holds at steady state, deterministic steady state, pick your parameters. Now you see, here's the Euler equation. Basically, what we're saying is that the expectation of this thing for basically any k, any theta, the expectation of this, where expectation is over the z, should be 0. Now, what are we going to do? Okay, first what we're going to do is the deterministic stuff. Now, by the way, there's sometimes when I read papers where they talk about doing perturbation stuff, they refer to theta as being shocks, theta as being part of the uncertainty. And I've seen expressions where they're perturbing the whole theta path. This is horribly confusing and just, I can't see what this is not the way to think about it, no. See, when epsilon is when epsilon is 0, you have a perfectly good deterministic model. And yes, the theta plus is going to deterministically evolve down to 0. It's going to be, because rho is going to be less than 1, so this is going to be constantly shrinking. So the model that I'm perturbing around is one where you have K, the capital X, and you have the theta productivity parameter. Sometimes I've seen it where they say, oh, here's a deterministic model, and then now I'm going to perturb it with respect to this whole process theta. No, that's horrible. That's awful. Way to think about it. No, first we examine the deterministic problem, where the deterministic problem has states K and theta. Okay. So first of all, what we're going to do is find out first order derivatives in the deterministic problem of the consumption function with respect to K and theta. So take the derivative of the Euler equation with respect to K, and then impose steady state. That means epsilon is equal to 0. Theta in the steady state is 0, by the way, and K equals 1. And so you end up with a quadratic equation in terms of the derivative of K. Solve it out. Stability tells us which one is the solution. And so then this is the solution here. This is the solution. Okay. Now let's do the same thing with theta. Let's perturb theta. Let's perturb the Euler equation with respect to theta and solve it out. And what we see is we end up with a linear equation in the derivative of the consumption function with respect to theta. Now, now notice, oh, by the way, in this first equation involving C sub theta, C prime with respect to K shows up. But then when we put in the solution values for that, then we end up with the equation for the theta derivative. Now notice this is linear. See, this is theta is an exogenous state variable. And so one doesn't have to think about this as a system of the vector K comma theta. See, at the steady state where theta equals 1 and epsilon is equal to 0, where theta is 0 and epsilon is 0, you just have the endogenous state variable, and then you have a Riccati equation when you linearize it. And then after that, when you perturb with respect to theta, you just get linear things. You don't have to come up with a fancy Riccati equation in K and theta. If you did, that's kind of a waste of effort. So now we do K and theta to 2D. So here's the second derivative with respect to K. We solve that out. This is the cross partial. Take the Euler equation derivative with respect to K and theta. Steady state, simplify it, blah, blah, blah. And now we find out what the cross partial is. And now here's your sum total number of solutions. Here's the second partial with respect to theta. Okay, we solve that. Now we're going to do third order derivatives. The third order with respect to K, and then second order with respect to K, and then with respect to theta, and then K theta theta, and then theta theta theta. Anyway, so we could go on forever, but we now have the when epsilon is equal to 0, we have the deterministic problem, where you have the capital stock that's moving around, and you have the theta that's also possibly moving around, but the two of them both end up at their steady state values asymptotically. Now comes the fun stuff. Now we're going to add in the uncertainty. part. So epsilon represents the standard deviation of the shock. So that means, by the way, epsilon squared is like the variance. You see, the variance of little z is 1. And so the variance of epsilon z is going to be the square, it's going to be epsilon squared. So the Euler equation, the true Euler equation condition is that this thing is, the expectation of this is 0. We're going to compute power series expansions of this integrand. So this is the integrand of the expectation. We're going to compute a Taylor series of this with respect to epsilon as well as k and theta. And then at each step, we're going to be imposing the condition that that power series is 0 in expectation. Now, by the way, we are assuming that you can interchange integration and differentiation. Okay? Because like the Euler equation, we want to take the derivative of, we want to compute the derivative of the consumption function. It, however, is defined involving an integral. And so when you take the derivative of the expectation of this, what we're going to be doing is taking the expectation of the integrand and then integrating that out. So we are interchanging differentiation and integration. Many macroeconomic applications of perturbation methods, even when they try to do things right, they violate this assumption. Now, this is easy to violate because suppose the random variable here is normal. Suppose it's normal. Now, when epsilon is equal to 0, this whole thing is killed off. And so we just end up with k and theta, and then we solve out for some function with respect to k and theta inside a box which contains the dynamic process. If I were to, if little z were normal, and then I make epsilon slightly positive, then the z becomes arbitrarily large values. So z can become minus infinity, positive infinity. So this becomes arbitrarily large. And so then what can happen here is that, see, the integrand, if you think of this as an integral over z, when epsilon is equal to 0, this is just an integral over a point mass. This is trivial. This is just a point mass. When you add z, the domain of the integral explodes. When that is the case, you have a singular perturbation, and things can easily go bad. There is a paper by Chris Sims and his some students of his, where they do, I think most of it is, they do some second order expansions, and most of it is correct, except they do ignore the fact, they love having normal random variables, and they ignore the fact that you have these infinite disturbance, possibly infinite disturbances. And so their approximation isn't valid. Now, by the way, there's no argument between Chris Sims and me on that. In the paper, this is KKSS are the initials, Kim, something, and Sanders, Sam Sims. In the paper, there's a little place where they say, Ken Judd has told us that this is not mathematically valid. We don't disagree, but we find this useful. So I guess that's to be written off, but typical macroeconomics behavior that, yeah, mathematical validity is not important. What's important is that something be useful. I take a very different attitude on that. By the way, those of you who are familiar in finance with the Campbell approximation methods and Campbell and Becerra book on this stuff, they make the same mistake. And so they do these expansions, and then they solve up for portfolios. And sometimes the portfolio will have you shorting many of the stocks as well as going long. And the result is that with some large shocks, your consumption, your portfolio, your wealth can go negative, and negative wealth doesn't have a value for log utility functions. So I was at a conference, I pointed this out to Becerra. He at first denied it. And then fortunately, Carl was at the seminar. And so I went to him and I said, give me your copy of the Campbell-Becerra book. So he did, and because I knew that on the top of page 28, there was some comment on their part saying that their approximation methods have problems. So I showed that to Becerra, and he just shrugged his shoulders and, okay, so I caught him. And then I asked him, so can you explain why this is okay? And he said, I have to go. There's a taxi waiting for me in front of the hotel to take me to the airport. So I guess that's how Harvard spends some of their $40 billion endowment, that they have taxis ready to swiftly extricate their economists if they're asked a tough question by me. So then off he goes, never having an excuse for why this is okay. So this is, now, by the way, in the early 70s, Paul Samuelson wrote a paper where he said, if you're going to talk about small noises, the noises have to be compact support. Paul Samuelson knew this and wrote papers making this point and using it back in the 70s. So now you'll see later, you might want, well, where am I going to impose a condition that the random variable z has to be bounded in support? You'll see that that's coming later. Now, what I'm going to do is there's going to be sigma is going to be normalized, so the variance is 1 of the random variable. Now, so what I do is I take the Euler equation that we have, Euler equation error, take the derivative with respect to epsilon, and then impose a steady state, and then plug it, but then we're going to have a lot of these derivatives with respect to k and theta, and then plug in their solution values, and we find that this is the case. This is true. So this is supposed to be equal to 0. It's not that this is supposed to equal 0, then simplification of this. It's that remember, what we're computing is the expectation of the integrand is supposed to be 0. This is the first order derivative of the integrand with respect to epsilon. So its expectation has to be equal to 0. Well, now, how do we take an expectation of this random variable z? Well, the expectation of z is 0. So we just replace z with 0. And we end up with this having to be equal to 0, which basically just says that this first order derivative with respect to epsilon is going to be 0. Now, that was a lot of work to get a trivial answer. But this is very much intuitive because epsilon represents the standard deviation of the shock, not the variance. Remember that in standard economics, in terms of risk premium and things like that, it's the variance that matters, not the standard deviation. It's the variance. Well, it's variance of standard deviation squared, yes, but what's important here is that it's not, epsilon doesn't matter. It'll be epsilon squared. Now you might say, why not just do this in terms of the variance? You can't do that because the problem is that there are going to be terms here involving the moment z cubed, which is skewness. And if you don't include, if you don't scale this in terms of epsilon, the standard deviation, then higher order terms are going to miss the skewness. This is what's called the gauge of the expansion. I mean, I know there's a variety of epsilons that you could plug in here and scaling them, but this is the right one for this. This is the right gauge. So now, by the way, the fact is that all of the cross partials of C with respect to K and theta, when the first derivative with respect to epsilon is going to be 0, so we just plug all that information in here. Now we're going to take the second order derivative with respect to epsilon, plug in all the solutions, and now then we end up with this being the equation for the second derivative with respect to epsilon at the steady state. Now we integrate this, well, gee, the integral of z squared, that's going to be the variance, and the variance we've set is equal to 1. And so now we have this equation oh, by the way, now there isn't a z here, but if there was a z left over, we set equal to 0, and then we have this now for the second order term. So what does this term do? This says that the whole consumption function is going to move by 0.05 per unit of variance. That's what this says. It's going to change the whole consumption function by a unit shift. Now we got to do the perturbations. Okay, this is second order epsilon, but now let's do the second order, which is a third order thing between K and epsilon, and we find that cross partial has that value. Theta epsilon has that value, and so we now have. So now what we have is third order Taylor series expansion around the steady state of K equals 1, theta equals 0, epsilon equals 0. And we have a third order expansion in those three variables. Okay. Now, how good does it do? So what I'm going to, basically I took all, this is a way to get the solution. So here is now the, well, it's a quadratic. Okay. Oh, okay. Unfortunately, I just took the second order Taylor series approximation. Okay, so, and I stopped. So then I then create now this is the important step. So I take the Euler equation error and I plug in the solution. Now that involves the variable z. And now I'm going to integrate out the Euler equation error. Now comes where what I'm going to do for integration. Well, I'm just going to say that z is a random variable, which is either -1 or +1 with equal probability. And so it's variance 1. And so now the integral is just a matter of, oh, I should divide by 2 here, by the way. Sorry, but that's just a scalar thing. So the expectation, I take this and divide by 2. And then now this now is a test for Euler equation accuracy, where I take the expected Euler equation error and divide by U prime C. And now at the steady state of the deterministic problem, so epsilon equals 0 and steady state theta equals 0 and 1, K equals 1, it does. So this thing works. It better work. Now I'm going to test just the deterministic part of this approximation, and indeed it does a good job. I mean, log base 10 errors are nice. Now, what about for okay, so now that was, you see what this was the deterministic problem where I held theta fixed at 0. So this is exactly the same kind of problem I did earlier. Now what I'm going to do is stay with the epsilon equals 0 problem, which is a deterministic problem, but now I'm going to look at the Euler equation errors over the k theta space. Because remember, this is the steady state here, where the steady state is down here. Theta equals 0 and k equals 1. This is a steady state of the k theta problem. But maybe theta starts with okay. Oh, yeah. Maybe theta maybe you start with a low productivity, and so then over time your productivity drifts upwards, and then your capital stock is also going to change. So this tells you about the k theta problem for a variety of k's and thetas, and the range and how well it does in terms of log base 10. Basically, I think this is like minus, log base 10 is -1 here, -2, -3. I should have that, include that in the label. Now that I'm going to add a small variance of 0.01, which I believe is bigger than typical business cycle. You see, the typical business cycle is like your standard deviation is like 0.02 plus or minus 2%. Yes, but of course we just got a big shock now. But so this is what the Euler equation errors are for a small business cycle, for standard business cycle. Notice that nowhere is equals 0. That's in white, but you know, now by the way, the thing is that if we simulated this, it's not likely the case that it's going to live around theta equals 1 and k equals 1. Theta equals 0 and k equals 1. The theta is going to go up and down, and the k is going to wander around. And so look at the theta, the Euler equation errors are very good. Now, this is a very high value for variance. This is very bad. This is like productivity either drops by 70% or increases by a factor of 2. Something. Anyway, this is a big shock process, and even then, it seems to be doing a decent job. And now then, I plotted out see, some people like to plot these things out. This is, you have a two-dimensional function, so you plot it out, and that way I prefer contour graphs. Contour plots tell me a lot more. Anyway, so that is how one proceeds. I mean, this example is very simple, trivial in many ways, but it takes you through the steps, step by step by step, of what you're really doing. Now, when you look at, for example, the package that Sims has that some people use, or Grohe-Schmidt, MATLAB code, you don't really get a good feeling for what you're doing, because they have you doing various, you compute Jacobians and then eigenvalue methods and all that. You don't really have I don't think you get a good idea about what's really going on. Now, for what they're doing, I think the Sims and the Uribe Grohe-Schmidt code is probably fine for the second order approximations, but you really don't get a good idea as to what is going on in the background. Why is that important? Because if you ever want to prove that this is valid, you have to proceed in this manner in terms of conceptualizing the problem. Also, even if you're not going to prove anything, it'd be nice that you document the quality, and that is, of course, not done in economics. Also, what happens, by the way, is that sometimes you get when you do this higher order Taylor series expansions, you get these crazy polynomials that describe the evolution of the system. You see, it's very good close to the determinants of steady state, but then it might go a little bit crazy away from there. That's fine, but then when you start adding a shock to it, the process may get kicked out to to where the Taylor series expansion is not valid, and then things go very wacky. And so then Sims and then other people like Uhlig have papers on what's called pruning, where they take a second order approximation and they kind of like prune the troublesome higher order terms. But I never understood. Wouterdenhaan has a very nice discussion of just how awful and incoherent the pruning process is. So, and again, by the way, this is fundamentally because they don't understand what really is the problem here. See, the right way to think about this is that your deterministic problem is a problem in a function space. You're trying to find some unknown functions, and they are pinned down by some operator. Now then, when you want to move from the deterministic problem to a stochastic problem where the epsilon parameter is not zero, the right way to think about it is that you're moving the entire see, the solution f of k comma theta is defined globally. And when you perturb epsilon, you're perturbing the whole system. You have to take a perspective of it that the epsilon perturbation is a perturbation not around the deterministic steady state. No, it's perturbing the problem around the function that defines the deterministic solution, and you're perturbing it in a Banach space. Now, I had a paper on this in the early 2000s, applying it to a game example. But that's the right way to proceed in terms of theory, is to really the perturbation here is not around the deterministic steady state. It is really a perturbation in a function space. And that's the only way that you're going to be able to proceed and use perturbation methods and have them be valid globally. Anyway, so that's, now, by the way, I wrote some papers on perturbation methods, as you've seen. And some of them actually get cited frequently, but what I don't like is that they then apply them where they're inappropriate, because most times people ignore the fact that there's a finite radius of convergence. They then go and simulate it using unbounded random variables, and then of course it's going to go bad. So no, perturbation methods are good as long as you take some care about validating them. I sent you the Jin and Judd paper. Unfortunately, we were doing nice stuff, and then he decides to graduate and get a job on Wall Street and all that stuff. But now in that paper, there is a procedure for examining whether or not your perturbation method is a good one, and even for the stochastic problem. And there's a procedure there that is then used in this symposium, JEDC symposium, for which I gave you the introductory paper. And so it's getting late, but I won't go into that. But the perturbation stuff is fine if you verify it. Like I say, trust but verify. And when people don't verify, I don't trust. Particularly when they tell me they have problems, things go bad. So that's why my more recent efforts have been on global solution methods, like you saw on Tuesday, because those are going to be more robust, solving a variety of problems. Okay, so I will wrap up. So this is the end of the formal lecture. Bye.